All right, so let's talk about the first chapter in this book, Machine Learning Landscape. We already covered a little bit of it in the previous thing. We're going to talk about types of machine learning models to set up. So machine learning is now in the old-fashioned programming. If you wanted to make something like a spam filter, you would have to write the code. So you would examine it, you would find words that appear often like credit card or something, then you'd write an algorithm that does something like count how many times a forbidden word appears in there, and then say if it had more than 5 occurrences of a forbidden word, it's spam or something, and you'd improve your code until it meets your standards and then launch it. This is old-fashioned coding, so you study the problem, you write rules, you evaluate, analyze errors, iterate around until you're ready to launch. This is how normal software development works. But machine learning is very different. You study the problem, you give some examples to machine learning and train it. You don't write the code that tells it what to do, you just have it learn from the data. And it learns until it gets to some degree of performance, then you test it to see if the performance is good enough, and perhaps you'll need to adjust it, come up with more data, change how it processes the data, change how the model is designed, and after it's good enough, then you launch it. The important thing is you didn't have to figure out what the rules were. The model learned how to do something like training a human worker or a dog to do something. It figured out how to do it based on your training, not based on you feeding exact rules to obey. So you could, for example, automate this training and evaluation so you could feed in fresh data and keep retraining it as new data comes in to keep it up to date on the new data. Subject to that issue I brought up before of catastrophic forgetting, one problem here is if you're training it on new data, it will tend to forget the old data, so that is an issue, but that might be what you want. I just want to stop the kind of spam that's coming in today, and I don't really need to stop the spam that came in last year because that's not coming in anymore. So training it again every week or every month might be fine. All right, and this works for complicated problems. Like speech recognition. In the 60s, people thought we could have speech recognition systems, but it turns out that people talk very differently. And especially if you consider men versus women and young people and people with accents, many different sounds are interpreted as the same word, and this turns out to work pretty well with machine learning. You just train it on all that, and it finds whatever's common in all those different sounds. Then you can help humans learn, you study the problem, you train your machine learning model, you inspect it, and then you get a better understanding of the problem. People are using it for science and stuff, to develop new drugs, protein folding and stuff. So it can help. So it's great for problems that are hard to do with existing solutions and complex problems, things with a lot of data or changing environments. It's useful for that. So you have classifying things for production lines, and these use convolutional neural networks or transformers, which we'll talk about a lot as we go ahead, to detecting tumors in brain scans, reading things like x-rays from these blurry, cloudy images. Machine learning models are often better than real doctors at doing that. Classifying news articles to summarize the trend. Are people liking this or not? That's natural language processing, and we'll talk about it. It's typically recurrent neural networks, but these days it's more often transformers that are being used for that, and we'll see in detail how they work as we go ahead. Then chatbots, detecting credit card fraud, sorting customers and recommending products and so on. There are many, many applications why everybody's so excited about it. So here's the basic types of systems. You can decide how they're supervised during training. You can decide whether they learn incrementally on the fly or whether they just have one training period and then it's done. And you can decide whether they compare new data points to known data points or just detect patterns, and you have instance-based versus model-based is a category we'll talk about. So training supervision, there's supervised, unsupervised, and a few other ones sort of in between. Supervised learning we talked about, where you pay a human to label the data, and now you have labels, and the model just learns to apply the label, and you know what the right answer is. So another supervised learning task is where you have some kind of measurement of something that depends on something else. So you have like the numbers of customers that buy something based on the price or something like that. So you have some kind of measurements, and then you try to fit some kind of curve to this. Unsupervised learning is where you just have a bunch of data and it has multiple parameters, but you don't know what the right answer is. There's no label to apply to it. So you can cluster it into groups or you can visualize it after you cluster them into groups and colorize it and help people understand categorize the data, which is of some value. Another big issue is dimensionality reduction. Consider, again, a Tesla. I have a camera that's probably high resolution, probably like 4K by 4K, and it takes many frames per second, like 30 or 60 frames per second. So I have, 16 megabytes of data coming in many times per second. And I'm trying to drive a car. That is a lot of data. 16 million parameters just in one frame, and maybe 100 frames in the last few seconds of data. So I have to analyze 100 times 16 million data points, and I have to do it really fast because I'm driving a car. If there's somebody walking in front of me, I have to step on the brakes right now, and I only have something like 1 second to make that decision. So how can you possibly process that many data points? And the same thing's true of the human brain. Your eye is high resolution like that too. So how do you know when somebody throws a baseball at your head to jerk your head out of the way? And the answer is your brain has a formation called, I think it's the amygdala, and it carefully processes the incoming data to figure out what part of that data is important. It throws away 99.9% of the data. And you only get the data that matters. So in fact, your brain is very good at detecting if something is going to hit you in the head. Your head jerks out of the way, and it takes about 50 milliseconds to make that calculation. And the Tesla can do it too, and they do it because of dimensionality reduction. You have to somehow simplify the data by throwing away almost all of it and keeping just enough data to do the job. Otherwise, you would never be able to get anything done. It is not true that you need to process every single pixel in your visual field to recognize something. Much less information is actually needed for a job. And so we'll talk about how that works. You do it with principal component analysis. And we've already talked about anomaly analysis, where you find things that look out, things that are exceptions, and you can discover interesting relations between attributes. We'll talk about this more as we go ahead. Then there's semi-supervised learning. We're going to do this in the projects where you have some data and you don't want to pay a human to classify it all. So what you do is first you break it into groups with unsupervised learning techniques, and then you just find the representative sample out of each group, and then you pay humans to label them. So by labeling only a few instances, you can get as much benefit, or almost as much benefit, as labeling all of it, because you group it together and then just find an exemplar of each group. This is quite powerful, and we'll do this in the projects. And then, of course, this technique we talked about where you make labeled data from unlabeled data by masking part of it. This is very powerful, and that's how the large language models work. Then there's another one, reinforcement learning, where you perform a task and then you're given a reward or a penalty. Like you play a game and it tells you whether you won or lost. And then you have to play a million games to practice and develop a technique. So you do it, and then at the end, you either get points, lose points, or you gain points by doing the right thing. So this is a lot of how you train animals, from giving them rewards or penalties for doing things. So let's try a Kahoot. I've got them here. There it is. All right. So go to kahoot.it and put in that number, and you can play the game. I'll record the winners. All right. All right. All right, so what part of the system learns and makes predictions? All right, that's called the model. The training set is just the input data. The model is what processes inputs and makes predictions. All right, what system might mask a portion of training images to generate a labeled data set? That's called self-supervised. You create supervised data from unsupervised data with masking. All right. All right, which system needs labeled data? That's supervised learning. You have to have labeled data to train it. It's easiest to understand how it works, but the problem is, of course, you have to pay for somebody to label that data. All right, and which system learns how to play a game based on rewards and penalties? That's reinforcement learning. You get positive or negative reinforcement after attempting the task. All right. All right. All right. So, all right, we've been here about an hour.